In our last lesson, we looked at area between curves. In this lesson, we're going to move on from area and look at volume of solids around a axis or a line. So what you can do is you can check out the GeoGebra demo. The link is given, and if this link for some reason is broken, you can always Google the disk method GeoGebra, and it should pop up the simulation you could use to understand what we're going to be doing here. So we've already seen that definite integrals can be used to find area, whether it's under a curve or between two curves. When we're finding volume, this is called the volume of a solid of revolution, and is always going to be revolving around a line, which is the axis of revolution. So for example, let's just say we have a rectangle over here. And if I want to rotate this around the x-axis or the axis of revolution, this thing is going to go all the way around and back up, which forms a disk. So again, you can see a arrow that shows that our rectangle is going to move around the axis of revolution. When that happens, this creates a disk. R is the height from our rectangle, and W is the width of the rectangle. Here's another picture you can take a look at. Let's just say that we're given this curve. A representative rectangle is given with some delta x. We're also bounded between A and B. Now, if we think about revolving this around the axis of revolution, or in this case could be the x-axis, this is what we're going to get over here. So if I take that shape that we had from that picture and revolve this around our x-axis, this entire shape is what we get. And if we try to approximate it by smaller and smaller disks, this picture is actually what we get, is approximation of n disks. So here's the method to find the volume of an object that is rotating around or revolving around an axis. If we are in relative to the horizontal axis, which could be the x-axis or it could be any horizontal line like y equals 1, then we're going to use this following formula. V is equal to pi, the integral of a to b of r of x to the power of 2 dx. And if we are revolving around a vertical axis like the y-axis, or x equals 2, x equals -5, anything that is a vertical line, then we're going to use this formula over here, which is v is equal to pi from some interval c to d along our smallest y value and the highest y value of r of y squared dy. So these are the two formulas we're going to use. It's important to note that the disk method is only used when the axis of revolution is completely connected to the region. That means you see this blue region here, our x-axis is connected to it, or the line is connected to it. Another important note, the rectangular strip is always perpendicular to the axis of revolution. So if you see here, this is our strip and it's perpendicular. This is our strip and this is perpendicular. So here are the steps in finding the volume of a solid using the disk method. First, we're going to draw a picture and shade in the desired region. Then we want to determine if the axis of revolution is completely connected to the axis of revolution. If it is, we can continue on and use the disk method. If not, we have to use an alternate method, which we are going to learn in the next few lessons. Then you want to draw an arbitrary rectangular strip perpendicular to the axis of revolution. This is going to represent one rectangle in the Riemann sum approximation. Then we want to find the expression for r, which is the radius of the disk. I find an expression for the distance between the outside of the region and the axis of revolution. In the fifth step, you want to find the area of the base of one disk by substituting your expression for r into the formula for the area of a circle. For example, if we're looking at the area of a circle, a is pi r squared. Then you want to multiply by dx if we have a vertical strip, or dy if you have a horizontal strip, to get the volume of one slice of the solid. Then we'll integrate over the interval to get the exact volume of the solid. For this first example, we want to find the volume of the solid formed by rotating the region in the first quadrant bounded by graph of y equals 4 minus x squared and the coordinate axes, and we're going to rotate around the x-axis. It's going to look something like this. I'm going to go to GeoGebra and show you what this is going to look like. So here is y equals 4 minus x squared, and this is what our graph looks like if we just focus on the xy plane. Now, if I want to revolve around all the way around, this is what our volume is going to look like, or our full solid is going to look like, so I can calculate the volume. Now, if I consider its length, width, and height, I'm going to move this around so you can see it kind of looks like almost not half a circle, but something that's rounded but flat. This is what we're trying to find, the volume of this shape. And this is just coming from that portion of that parabola. So again, this is the front view of it, and I can get rid of the shaded in parts. This was our original graph, and this is us rotating around the x-axis. And here's a 3D version of what we are trying to find, this volume. You can use this same GeoGebra page and do other functions if you want to. So you just plug in your function here. These are your bounds over here. And this is how much revolution you want to go through. So this is the full 360 all the way around the x-axis. Now going back to your notes, because since we have a better idea of what we're trying to find, our first step is to draw a picture and shade in the desired region, and we already have a picture given to us, so we don't need to worry about that. And moving on to the second step, we want to determine if the axis of revolution is completely connected to the axis of revolution, and it is, because it's attached to the x-axis. It's also attached to the y-axis if we wanted to use that. Then we want to determine the rectangular strip that's perpendicular to the axis of revolution. So here is our arbitrary strip that's perpendicular to our x-axis. Now we want to find an expression for r. Well, we know that the shape here is coming from the equation 4 minus x squared. And the bottom part of our shaded area is just the x-axis, which is y equals 0. So we want to find, it's almost like the top minus bottom that we've used when we're finding the area. So our top function is 4 minus x squared. Our bottom function is just y equals 0. So overall our r is 4 minus x squared. Then our next step is to take this r and put into our formula. So we're revolving around a horizontal axis. So this is the formula that was given to us from above. And this takes on the form of pi r squared. You have your pi, your r for your radius, and we're squaring it here. We found what r is already, so we're going to put that in. If you take a look at our bounds along the x-axis, it's going from 0 to 2. Okay, so this is what we're trying to integrate. So take a note that this is the left x value, and the 2 is your right x value. And if we were to plug this into the calculator, we're going to get 53.62 is our final answer. And if we go back into our GeoGebra, that's what we're given right here as well, 53.62. Moving on to example 2. Want to find the volume of the solid formed by rotating the region bounded by the x-axis, y equals the root of x, and x equals 4. Okay, so we already have the picture here. We can draw the slice if we want to, or we can go ahead and think about what our radius is going to be. So according to a formula, we have pi, the integral of a to b of r of x dx with r of x squared. So let's think about our r here. Well, we have a top minus the bottom. So the top minus the bottom is going to be the root of x minus 0, because our line is the x-axis, which is y equals 0. Okay, and then our bounds, we're looking from here to here, which is from 0 to 4. We're going to plug in r of x, which is root of x squared dx. This one we can just do by hand instead of using our calculator for that. So this is from 0 to 4 of x dx, and then we can integrate that, which is x squared times pi over 2, evaluating from 0 to 4. So that's pi over 2 times 4 squared, which is 8 pi. Is our final answer. Example 3, want to find the volume of the solid formed by rotating the region in the first quadrant bounded by the root of 16 minus x squared. And we're going to do this around the y-axis now. So this is our line for rotation. And when we read this, it's going to be from right to left, right minus left, to find our r. So we want to do right to minus left to find r. Our most right is going to be the root of 16 minus x squared, but we are going to integrate in terms of y, so I'm going to rewrite this as x is equal to 16 minus y squared. That is when you square both sides, move the 16 to the other side, and then square root again. So our most right is the root of 16 minus y squared. Our most left is the y-axis, and that is x equals 0. So r is just going to be the root of 16 minus y squared. Your volume is calculated as pi from c to d of r of y all squared dy. So RC in this case is going to be from 0, and our d is going to be 4 because I am reading off of our lowest y value to our highest y value. R of y is 16 minus y squared. And then you could integrate this. You could plug this one into your calculator if you want to find the final answer, which is about 134.041. We'll go through two more examples. In example 4, we want to find the volume of the solid generated by revolving the region bounded by the graphs of x, y is equal to 6, y is equal to 4, x is equal to 6 around the line y is equal to 4. So because we are revolving around a horizontal line, we are going to use this one. And when we figure out our R, it's going to be top minus bottom. So if we take a look at our top, is going to be the line y equals 4. And our bottom is this x, y is equal to 6. Now I want to rearrange this and solve for y because I want everything in terms of x, so I can integrate in terms of x. So equivalently, this is going to be 6 over x. So then bottom is going to be 6 over x is our equation. That's our R. Now we're going to plug it into the formula. Our bounds are from left to right. So our most left is going to be, looks like 1.5. And the highest x value is going to be 6. So we're going from 1.5 to 6. 4 minus 6 over x all squared dx. Again, put this into your graphing calculator so you can find the integral. This is 73.695. Then for example 5, we want to find the volume of the solid generated by revolving the region bounded by the graphs. The same one, x, y is equal to 6. Y is equal to 4, x equals 6, but in this case you're going to go around this line. So we're going to go around a vertical line. We are using the integral of c to d of r of y squared dy. So we need to find our r, and we're going to find r by doing right minus left. So our most right is going to be the line x equals 6. And then our most left is going to be this one over here, this line, or this equation that we can get from x, y is equal to 6. Remember, we want to differentiate in terms of y, so I'm going to solve for x. So we can get 6 over y, so minus 6 over y. Now we're going to go ahead and plug into our volume formula. Because we are integrating with respect to y, we're going to look for the bottom y value to the top y value. So our most bottom y value is 1. Our most top y value is 4. I'm going to put in the r that we found and then integrate. So this will be about 110.543 as our final.